Hi, everyone. This is Susan Nash, and I'm with AEPG. I'm just absolutely thrilled today to have a webinar that people have been waiting for and clamoring for because it's potentially a huge game changer for the actual planet Earth in terms of our energy resources. Now, that's a lot of enthusiasm. I realize that, but the potential is amazing. So we're going to be talking about geologic hydrogen today, and we have Geoff Ellis, Energy Resources Program at the USGS, US Geological Survey, and we have Evan McIntyre of Hytera, and they are based in Australia, but they are currently drilling in the Nemaha Ridge in the mid-continent in the United States. So I'd just like to thank everyone, and I'd also like to take a moment to recognize the Division of Environmental Geosciences. They are sponsoring this, and we have some commercial sponsors as well. So I would just like to take a moment to recognize Capstone, CSR, Heath, Purvis Energy, Well Done Foundation, and Zafiro Methane. So we have 6 wonderful sponsors. So really want to thank them as well. So anyway, before spending any more time with intros, I'd like to go ahead and turn it over to Geoff Ellis. So welcome.
Thank you, Susan. Yeah, it's really a pleasure for me to be here today. Really excited to talk about this. As you said, this really has the potential to be a game changer for the energy landscape. And so what I'll do in the time that I have with you is to start out with just a very high level overview, some background and some discussion of what we know and don't know about the potential for natural hydrogen, and then move into a very brief overview of some of the more interesting developments, the most recent developments, and where I see some potential for upcoming developments in the next year or so. So probably most of you are aware by now that natural hydrogen is ubiquitous on the surface of the Earth. It's in the air that we breathe and in soils, and the world's oceans are super saturated with respect to hydrogen. And in some places, fluxes of hydrogen coming out of the subsurface can be quite large. They've measured on the orders of thousands of cubic meters of hydrogen-rich gas coming out of large regions of the Earth's surface. And it's not just a surface effect that very frequently in deep boreholes or underground mines, we find high concentrations of hydrogen gases. But one place where we very rarely find hydrogen as a molecular hydrogen gas is associated with oil and gas. We've drilled hundreds of millions of oil and gas wells around the world, and it's really quite rare to find more than about 1% volume percent of hydrogen reported associated with gases in these petroleum systems. And so for this reason, we've assumed that hydrogen can't form accumulations, that the rationale being that the molecule is so small, it's quite diffusive, and so it's difficult to trap, and it's also very reactive, both in terms of biological processes and abiotic processes. So although it's around in the subsurface, we've always thought that you simply can't form accumulations of hydrogen. But there are some good reasons to question this interpretation. The first being that the petroleum exploration is not targeting at natural hydrogen. So I think it's a bit naive for us to think that if we're not looking for hydrogen, that we should just be finding it accidentally all over the place. And importantly, oftentimes in oil and gas exploration, they don't analyze for hydrogen, especially historically. Throughout much of the 20th century, hydrogen was used as a carrier gas. Gas chromatography, which we use to analyze gas compositions. So we couldn't analyze for hydrogen. We needed to do specialized analyses. And oftentimes they simply wasn't done, or it wasn't reported. Companies did, in fact, sometimes find hydrogen and it just wasn't interested and walked away from it. More importantly, I think, too, is that the geologic settings where hydrogen is most likely to occur are not necessarily the places where we are actively exploring for oil and gas. Hydrogen is generated through water-rock interactions, either through radiogenic processes or redox reactions involving iron minerals. And these are often not places where we're exploring for oil and gas. Additionally, the process of generating hydrocarbons is actually hydrogen limited. When we measure the richness of a petroleum source rock, we measure the hydrogen content, the organic hydrogen content, which we refer to as a hydrogen index. And so if you have an external source of hydrogen that's migrating through the subsurface and encounters an organic rich rock, that hydrogen is very likely to get incorporated into hydrocarbons. And so we really shouldn't expect to find much hydrogen gas actually with natural gases. Now, it is a fair point that mineral or mining companies often are exploring in some of these hard rock settings where we would expect hydrogen to be generated and potentially accumulating. But mining companies very rarely measure gas composition. If they're measuring gases at all, it's from a safety perspective. And so they don't actually look at the composition of the gas. So they don't know if it's actually hydrogen or methane or something else. And these ideas are not unique to me. In fact, these arguments were actually put forward more than 20 years ago by Nigel Smith and colleagues at the British Geologic Survey, and this is just a one book chapter that they published. But unfortunately, at that time, this concept was pretty much overlooked. And it wasn't until 2012 where we had an accidental discovery of an accumulation of nearly pure hydrogen gas in the country of Mali in West Africa. They were drilling for water and encountered some flammable gas in a quite shallow reservoir. And subsequently, when they measured the composition, discovered that it was in fact almost pure hydrogen. And they followed that up with an extensive exploration campaign and have since delineated at least 5 reservoirs that are charged with nearly pure hydrogen gas and potentially has as much as 670 billion cubic feet of natural hydrogen stored in an accumulation. So as news of this discovery has gotten out and reached the broader geoscience community, we've seen a growing interest in exploration for natural hydrogen as a primary energy resource. It's spread to other parts of Africa and Europe, and as well as into South America and quite a bit into Australia. These countries listed here are not, it's not a comprehensive list, but these are some of the areas where much of the activity is going on. And the first wildcat well that was drilled explicitly looking for natural hydrogen was drilled here in the US in the state of Nebraska a few years ago. And the company now is working on flow testing the well to see what type of production they might get. And exploration in the US has now spread to other parts of Nebraska as well as other states such as Kansas and Montana and Arizona. Importantly, there were some announcement of a major discovery on the York Peninsula in South Australia just last month, where the company called Gold Hydrogen has drilled into a place where there was some historic record of hydrogen concentrations in the subsurface and confirmed those concentrations. And I'll talk about that more a little bit later. And then I also want to mention that here in the USGS, we've begun a project where we are working now to map out where are the prospective places for natural hydrogen resources in the United States. And I'll come back to that point as well in a bit. But I want to come back to or come to this question about what could really the global resource potential be. This is a question that has plagued me since I first started thinking about natural hydrogen as a resource, and it's a question that I commonly get. And so to put things into context, the projections for the demand for hydrogen going forward are that it will probably increase by perhaps 5-fold to meet the demand to decarbonize the so-called hard to abate carbon emissions. And so by 2050, it's thought that the demand may be as much as 500 megatons per year. There's been some recent studies that have looked at what the global production of natural hydrogen in the Earth's subsurface might be. And that amount is about 23 megatons per year. And so to put that into perspective, then, if we could actually find and produce all of this natural generation of hydrogen, that would only account for about less than 5% of what we think the global demand will be in the future. So it would seem that would not be really a very significant resource to go after. But we have to keep in mind that the resource potential is not just dependent on how much is being generated every year, but in fact, how much could actually be trapped in the subsurface, how long it could be held there. Would it be in fact consumed by biotic and abiotic processes? And how successful could we be actually in finding and producing this? And so in order to try and get a sense for what the magnitude of the resource might be, I started some work with a colleague of mine here at the USGS to see if we could put together a simple box model that would give us some sense of what the order of magnitude of this resource might be. And so this cartoon shown here on the upper right shows the components that we have in our model. We start with this an amount of hydrogen generated at the subsurface. And then hydrogen, as it's generated, will migrate towards the surface. Some of it will go straight up to the atmosphere, while some will get held up in traps. And then even as it's in a trap, some will leak out or get consumed over some period of time. And as hydrogen moves to the subsurface, it will be consumed by biotic and abiotic processes. And then we have some flux to the atmosphere, as well as then hydrogen that we could produce from our exploration activities. And so not all of some of these components are actually have been studied for hydrogen, and fair amount of them. Many of them are not constrained by specific studies to hydrogen, so we can use analogs, things from what we know from petroleum systems or from helium, for example, that we can put some constraints on these various components. And then we can assume that today the natural system is sitting here at steady state, and we ran a range of input values for each of the components of the model, and then run a Monte Carlo to see how much might be actually in place. And so when we do this exercise, the result we get is shown in this histogram in the lower right, and the range of values is quite large. It ranges from maybe thousands of megatons of hydrogen to tens of billions of megatons, with the most likely value on the order of, say, tens of millions of megatons. But we need to be very careful about interpreting these results, because this is a global model for the entire Earth's crust. And so clearly much of this is going to be inaccessible. And by that, I mean that it's going to be simply in accumulations that are too deep or too far offshore, or they're too small to be economic. And so they would never actually be producible. But if we imagine that just a small percentage, if 1% of that 10 million megatons could be recovered, that would represent 100,000 megatons, which would actually supply all of that 500 megatons per year for 200 years. And so I think the key here is that it's very likely that there is a large amount of hydrogen in the subsurface. And the question is it in accumulations, and can we find these accumulations? And so to get at that, we need to come up with a workflow and some conceptual models for how we can understand the accumulation of natural hydrogen. And so I've been working with colleagues in the USGS on developing a hydrogen system model. I think other companies are also actively working in this area, as well as other academic institutions. And in general, it's based on the concept of the petroleum system, where we have source, migration pathway, reservoirs, traps, and seals, so forth. And while it's tempting to try to just directly take the petroleum system and apply it to hydrogen exploration, we know that won't work. That there are some important differences that we need to account for, and so we have to modify the petroleum system to develop really an effective hydrogen system model. So what are those differences? Well, this is a list of some of the differences and similarities. This is not a comprehensive list, but some of the big issues that we have to keep in mind. So the first one being the source rocks. For petroleum resources, we're looking for organic rich rocks. For hydrogen resources, we're looking for iron-rich rocks that could then be oxidized and reduce water to generate hydrogen. Also, radiogenic rocks that have the capacity to generate hydrogen through radiolysis. And deep crustal faults have also been implicated as a potential source for bringing fluids up from the mantle and potentially the core even, that could be rich in hydrogen. And there are other source rocks that have also been suggested. Secondly, the rate of generation for natural hydrogen can be significantly faster than hydrocarbon generation. Hydrocarbons, of course, take millions of years to generate in nature, and we can actually observe hydrogen generation in natural settings like mid-ocean ridges or in the laboratory on timescales of days, in fact. Now, hydrogen is more mobile, more diffusive, as we've already noted, and so it will have a different. It's more difficult to trap, say, than hydrocarbons. But it's actually the size of a diatomic hydrogen molecule is about the same size as a helium atom. So helium can actually be a good analog for understanding the trapping and sealing behavior of hydrogen in the subsurface. There's also important differences between the solubilities of hydrogen and methane in water that we need to account for. And of course, this reactivity question of biologic and biologic processes that can really consume large quantities of hydrogen. But there are also a lot of similarities between hydrocarbons and hydrogen. Things like the migration processes are really primarily driven by advective flow, where fluids follow the path of least resistance. And so we can use tools that we've developed for understanding petroleum migration to directly understand how hydrogen might move through the subsurface. Reservoir quality is fundamentally going to be determined by porosity and permeability, similar to what we understand from petroleum systems. Trapping mechanisms and timing and preservation also could also be similarly applied to both petroleum and hydrogen. We also have to think about how we might produce hydrogen. This has implications for how we understand the hydrogen system. And there are three models that have been proposed for how we might actually exploit natural hydrogen resources. So the first one is what I refer to as natural accumulations. And so this is really analogous to the petroleum system, where you have a source. Say in this cartoon example, it could be olivine-rich rocks that then reduce water and generate hydrogen, and it migrates through the subsurface and gets up into a porous rock where you have an effective seal, and you form an accumulation there. And so in this sort of scenario, we need a source, a migration pathway, reservoir trap seals, preservation, and timing all come into play. But some people have proposed that because the rate of generation of hydrogen can be so rapid, that it's possible that we might not actually even need to find these reservoirs, these accumulations, that in fact, we may be able to drill down into a rock that's actively generating hydrogen, or a fault zone that has a flux of hydrogen coming up from the subsurface, and produce it as it's moving through the subsurface. And in this case, we don't need to worry about reservoir traps and seals, simply a migration pathway potentially, or the source. And then a third possibility is this notion that we could actually stimulate hydrogen generation. And so there are clearly a lot of lithologies in the subsurface that have the potential for generating hydrogen, but of course, not all of them are actively doing it or have done so in the past. And so we could, there's a variety of different methods that could be applied to try and actually stimulate the generation. An obvious one would be to simply drill down into an iron-rich rock and inject water into it, and allow that water to be reduced to hydrogen, and then recover the generated hydrogen. And so in that situation, we only need to understand where the source is in order to understand where the resource might be. But I think it's really critical to point out that the viability of the natural generation and the stimulated generation is really unknown. These are really hypothetical concepts right now, has never been tested. And the global model numbers that I showed you, this potentially tens of millions of megatons of hydrogen, that's only for these natural accumulations. And so if we could actually realize some of this other generation potential, then the total resource potential may be significantly larger. So as I mentioned, in the USGS now, we are working on doing some prospectivity mapping, and this is a cartoon diagram of the model now that we have built to account for the hydrogen system, where we have a number of different sources for hydrogen, and then we account for the migration of that hydrogen away from the source, and then we have other risk factors like the presence of organic rich rocks that could consume hydrogen, or the migration distance is important for potential for loss of through abiotic or biotic processes. And then we are accounting for reservoirs and traps and seals, as well as risk for preservation of accumulations through things like fault activity. And so we're currently working on acquiring proxy data sets for each of these model inputs, cleaning up the data sets and putting them into this model, and then working on calculating a prospectivity. Additionally, we're also are working on accounting for uncertainty, all of this, with a number of different approaches that we're looking at. One of them being potentially looking at a fuzzy logic type of approach, as shown in this cartoon here. And ultimately, our plan then is to put out an interactive web-based map. We think that there's so much uncertainty around understanding hydrogen systems that any static map that we were to produce today would be outdated within a matter of months likely. And so a much more useful approach, I think, is to have something that's interactive that users can adjust their understanding, the model based on their understanding of what they think is most important, as well as we will be able to then update this map as we get new data and new understandings going forward. And so this is just a mock-up. The data here are not real. Please be aware of that. This is still a work in progress, but I just want to show you an example of what we intend to put out, where we have the components of the hydrogen system, and then users would actually be able to interact with the map. So, for example, if you thought that a deep source of hydrogen was not really a viable thing, you could actually turn off the deep source, and the map will update and show you the prospectivity without a deep source. Or if you wanted to look at the weighting of serpentinization and see how important that might be, you can click on the settings button, and then this will show you how we in the USGS have weighted serpentinization as a source. But then you could actually update this, change this, and the map will then update based on your own interpretation. And then you could go back to the prospectivity map, and it will update and show you the new model that we put together. So this is a product that we're currently working on. We hope to get this out early in 2024. So I encourage you to come back and look back at the USGS website for more updates on that. And now I just want to finally just highlight a few of the recent activities and upcoming activities that I see as important developments around natural hydrogen resources in the globe. And so one point I want to mention is the recent test in Burake Bugu in Mali, which is where this first hydrogen accumulation was discovered, and there's the initial discovery well has been on production now for more than 10 years, and just last year they replaced the hydrogen that was being produced there was going to an internal combustion engine to run a generator to generate electricity for the village. But just earlier this year, they replaced that engine with an electrolyzer, and they're now been flowing hydrogen directly from the well into an electrolyzer, and they have demonstrated that without any further gas separation or cleanup, that they're able to generate electricity directly from a natural hydrogen accumulation. So that's really a major milestone in my view. Also, as I mentioned, we have these recent discoveries announced from the York Peninsula in South Australia. The company Gold Hydrogen has drilled the Ramsay 1 and 2 wells, where historically there were records of hydrogen in excess of 70% in some early exploration wells about 100 years ago. And they just last month went back in and drilled step-out wells near those historic wells and found very similar concentrations, suggesting that the gas in there is actually representative of a reservoir, an accumulation that has been in place, at least for 100 years now. Also of note is plans for next year for the first pilot project to stimulate hydrogen in a natural setting that's planned for the Samail ophiolite in Oman that should be happening sometime in 2024. And then also here in the US, there's plans for new drilling in the state of Kansas along the Nemaha Ridge that we're going to hear more about that from Avon in just a minute here. So just to summarize then, I think that there are very large quantities of natural hydrogen in the subsurface. And the real question is simply, what is the potential for that hydrogen to be in economic accumulations? And I think there's going to be a lot of interesting developments coming up in the next year. We at the USGS will be putting out our map of prospectivity for the lower 48. We should be getting results from flow tests of these wells from South Australia. Hopefully there will be this stimulated hydrogen pilot project taking off in Oman next year, and some new drilling results coming out of the Nemaha Ridge. So a lot happening in this space, and I encourage everyone to stay tuned and listen to what's happening. So thank you very much. With that, I will turn it back to Susan.
Well, thank you. That was a great overview, and wow, wonderful. Makes me have a lot of questions too. Anyway, so I'm really happy to be able to introduce Evan McIntyre, and he will take it away.
Thanks, Susan. I'm good to go, am I?
Yes, looks great.
Thanks. Okay. Well, thanks, Geoff, for the layup. Geoff's mentioned the Nemaha Ridge a bit in Kansas, which is an interesting location. So just as a bit of a preface, hi Tara, we're an Australian-based hydrogen exploration company. We've got leases on the Nemaha Ridge in eastern Kansas there. Now, we're a long way away from being able to write the textbook checklist of how to explore for hydrogen, but I've got to make a start somewhere, and a great place to start is where hydrogen has already been observed in historic wells, and that's the case for both Mali and also in the York Peninsula. And on the Nemaha Ridge, there was a bunch of wells drilled in the 80s, which all had some sort of hydrogen concentration. And on the screen here, you can see one of those wells, Scott 1, which has had various analyses done to it over the years, because you can see it's got a wellhead still extant at the surface. Occasionally, samples have been taken, and hydrogen continues to be observed in that well. Now, we know very little about the well. There's no logs available for it. We only know the depth, and that the fact that there's some hydrogen in the headspace of the well. So it hasn't been flow tested. It hasn't been really taken much further than just some analyses taken from the wellhead over time. So it's a great place to start. And we're going to use some of the data from this well to sort of unpack some of what we think we know about hydrogen exploration, and step back a bit and see if we can backfill the story as to why there could be some hydrogen in these locations, these historic wells, that we can backfill some of the subsurface story and understand, maybe we can even get to a predictive model as to explaining why we see hydrogen there. Oops. So in the Midwest of Kansas, which is right in the central part of the USA there, we have a bunch of occurrences. We can see a map here, which has got the Bougie gravity map of the US, overlain by some green dots. Now, the green dots are wells from the USGS gas database, plus a few others, which have been scaled for the hydrogen occurrence. So these are all wells that have been drilled and some sort of gas has been recovered from that well. And you can see that there's quite an interesting cluster of large circles there in eastern Kansas, which draws your attention and says, well, what's all this about? So also, the Midwest is an interesting place internationally, really, because we have very easily accessible acreage. We can get after things quickly with an existing service industry. There's off-takers nearby, so there's a lot of reasons to get excited about some of the locations in the Midwest of the US for hydrogen exploration. So, given it's AAPG talk, it's kind of easy to think that we can just quickly modify our existing petroleum system elements model a little bit and think about just repurposing that for hydrogen exploration. But I want to step back a bit and think about exactly what we need to think about and what we need to look at in this area. So the way I'm going to structure this talk and where I'm going to start is looking for the coexistence of three things. So we're looking at what's happening with our subsurface water, because ultimately water is the source of hydrogen in most exploration models. We need to look and think about the hard rocks, which are the catalyst for hydrogen generation. And we need to think about soft rocks, or the sedimentary pile, which is where we would like to think we can find an accumulation of hydrogen. And we kind of need to think about these things equally. Just concentrating on the overburden is probably not going to be enough. We need to understand the actual processes which are happening and how they all interact with each other. So I've got some equations here on the screen. You've probably seen these before, but the two main mechanisms for generating hydrogen, as Geoff referred to earlier, is water interacts with iron-rich rocks. The iron oxidizes and reduces the water, and we get hydrogen released. And then we have radiolysis, which radioactive energy splits the water molecule up into its component parts, and they reassemble, and we get some hydrogen coming out the other side of the equation. But one thing I'd like to point out with some of these equations is that we actually have water on both sides of the equation because it's a partial reaction. So water is coming into the reaction site and it's also leaving the reaction site. So water is something we have to think about a lot. And I'll get into why that is in a minute and what that looks like in the Eastern Kansas example. So starting off with water, it plays multiple roles. It's the source of hydrogen. It also transports hydrogen. When you're dealing with confined aquifers, which are interacting with iron-rich rocks, we need to think about what is happening to that hydrogen post-reaction, and it's usually in a confined aquifer. And also that water can be a host for methanogenic biota, which then transform the hydrogen back into methane. And often what we observe in some of these environments is that you get biogenic methane in very, very old rocks, and that's thought to be something to do with the juvenile bacteria in the water column. Anyway, looking at the lower 48, and we can see the drainage map here, which I've swiped off the internet. You can see the Mississippi River Valley catchment, which is bounded by the Rocky Mountains in the west through to the Appalachians in the east. And Kansas is smack bang in the middle of this map. So we can see that generally speaking, the water in this part of the US is flowing from west to east, both on the surface and in the subsurface through the sedimentary rocks there. And this is very important because it allows us to think about what our movement of hydrogen in the subsurface is by using water as a proxy. So we look at some of the aquifers in the area. We have multiple aquifers. So here we have a cross-section running the width of Kansas through to Missouri. It's about 600 miles or about 1,000 kilometers from one end to the other of this cross-section. We've got some shallow aquifers within the sedimentary pile, which support the local agricultural industry. But what is of interest to us is the deeper aquifers, particularly the Western Interior Plains aquifer, which scoots along the top of the basement and at the base of the sedimentary pile, and then gets forced up dip as it approaches eastern Kansas and into Missouri. And this is within our play level, so we need to understand what's happening here. So we look at a bit more of a detailed map for Kansas particularly, and we have basement here in yellow, and you can see how that deep Western Interior Plains aquifer in purple is bumping along the various highs and lows of the basement. We see two features here. We have the Central Kansas uplift, and then the Nemaha Ridge is a sharp little basement high further to the east. So the aquifer is moving from west to east due to the hydraulic head from the Rockies through to the drainage, and as it's moving along, it's picking up and interacting with the basement rocks, and it can both be entraining gases that it generates along the way, and those gases may dissolve and exsolve as pressure and temperature and salinity and the other things change particularly on this eastern flank of the aquifer system as it gets forced up dip, and what is in solution at depth may not be in solution anymore as it gets forced up dip and degasses. Moving on to hard rocks. So the dominant feature that you can see on the gravity map here is the mid-continent rift, which is a slightly over 1 billion year old failed rift, roughly similar dimensions to the East African rift. It crops out of the surface up near the Great Lakes and then gradually gets buried deeper and deeper as you get down into Nebraska and Kansas. And this is our primary candidate for hydrogen generation catalyst due to the iron-rich olivines and other unstable iron-rich minerals within that within that in that feature. And so the Western Interior Plains aquifer passes over and through this feature as it's transported from west to east through the subsurface. So if we look at the basement structure in the area, what I've done here is drape basement topography on some structural features. And so the Nemaha Ridge is this basement high, which runs pretty much north-south across the eastern part of Kansas. And it continues northwards up into Nebraska, and it peters out sort of around about the Omaha area. And it formed about 300 million years ago, and it's overlain by sedimentary basins which have been affected by it. And we don't actually see the Nemaha Ridge crop out at surface. It's always covered in sedimentary cover. And if we look at the map at the bottom there, we can see we've got this large fault system running on the eastern edge, the Humboldt Fault, which is a bunch of mainly sinistral strike slip faults extending from south to north along the eastern edge. Now, the mid-continent rift system, which was the large gravity anomaly I showed you earlier, is on this lower map here marked as MRS, and you can see it sits just on the western flank of the Nemaha Ridge and running down sort of roughly the central parts of the Salina Basin, which it underlies. So looking at the sedimentary cover here, we have a series of Cretaceous down to Cambrian basins. It's pretty well understood. It's typical Midwest basin geology there. We've got a mixture of sandstones, shales, limestones, and a lot of dolomites. And to the west, there's some salt. So there's multiple reservoir seal pairs within the succession. And so we know quite a lot about this succession through drilling through the Midwest. Unfortunately, there's pretty patchy seismic coverage, and there's no open file data system in the US. So trap definition is a bit of a challenge, but generally speaking, overall, the Nemaha Ridge forms a large focal mechanism for any subsurface gases in the area, and it can be treated as a giant trap in some ways, with further definition required. I've put the Nemaha Ridge location on the inset map there, running north-south through Nebraska and Kansas. And you can see that it largely is outside of oil-producing or gas-producing areas in a thermally immature Salina Basin, which is a very important factor in this instance. So looking at the stratigraphy for the area, we've got about 1,000 to 3,000 feet of sedimentary cover, and it's thermally immature for hydrocarbon generation. We have multiple reservoir seal pairs. You can see in the lower part of the figure, we have the what I've colored in purple is the pre-Pennsylvania succession, which is got multiple reservoir seal pairs in it and a mixture of siliciclastics and dolomites as well. We have this feature, the Pennsylvania nonconformity, which is related to the Nemaha uplift, which tracks across the area. In some places, removes that pre-Pennsylvania stratigraphy completely. So your objectives change depending on where you actually are on the ridge, and also the number of targets you might be able to encounter in the sedimentary section. Basement can be all sorts of things. It's often mid-continent rift fill or the flanking sedimentary fill related to that, or there's crystalline granites and plutons and so forth in the surrounding geology as well. So looking at the petroleum systems in the area, it's very interesting. Generally, petroleum systems are absent on the Nemaha Ridge. There is long distance migration from the Woodford Shale down in Oklahoma, where the source kitchen is, and migrates laterally up the Nemaha Ridge, and also the central Kansas uplift there to the west. And so as a result of this, we have pretty minimal contamination of hydrocarbons in the system, particularly gases, with the non-hydrocarbon gases that we see in the subsurface there. There are some oil fields along the Nemaha Ridge, as I mentioned, but they're long distance migration and don't really have any interaction with the hydrogen system that we can predict there. If we look at some of the the gas compositional analyses which have been done over the years. So 2 wells are particularly well known, which are Scott and Hines on the flanks of the Nemaha Ridge. And as you saw on the opening slide, since the wellheads are still there, people have gone back and sampled them over time. And the hydrogen concentration, which is the first green column on this figure, seems to remain fairly high over time. Now, because hydrogen is an extremely reactive molecule, wants to turn into other things, wants to escape, and so forth, we have to carefully consider the sample handling, the transport, exactly what happened to that sample and how it was analyzed over time. And so what I've done here is looked at what I consider to be the most reliable analysis on this table, which is a couple of samples taken in the early 80s, which were then taken to University of Kansas, which is about 100 miles away, and done at the chemistry lab there. So hydrogen is a difficult gas to sample and to keep a representative sample from well site to lab. So what I've done is selected that most, what I consider to be the most reliable analysis. And you can see, interestingly, when we look at the carbon dioxide and the methane composition in that gas mixture, it's very low. It's sub 1% anyway. So we've got a hydrogen concentration of around about 50%, and that seems to continue through time. So this suggests that that there's no influence from the thermogenic hydrocarbon system, and methanogenesis doesn't seem to be occurring for some reason in this location. Or maybe the hydrogen charge is continuous and we're just replenishing, or all of the above. As we get increasingly interested in subsurface hydrogen, I think we're going to be spending a lot more time looking at the carbon content of the gas mixture in which the hydrogen is found, because there's very little point in going after hydrogen in the subsurface if it's only a minor component of a carbon-rich gas, because it defeats the purpose of looking for it in the first place. You might as well just go for the methane if you're not concerned about your carbon concentration in that gas. So that's one of the things that makes the Nemaha Ridge area unique. So putting it all together, this is a play diagram which has been rattling around for quite a long time, and we've just redrawn it really. So we can see over here on the left of the image, we have the Rocky Mountains and the water recharge, and we have the various aquifers tracking through the sedimentary pile. And we have the hard rocks in brown, and in the western part of Kansas, we don't have much hydrogen observed historically, and we think that's because the mid-continent rift is located between the central Kansas High and the Nemaha Ridge, and that's where the source kitchen probably is. And then immediately to the east of the mid-continent rift, underneath the sedimentary pile, we have the Nemaha Ridge popping up, and that's where the 10 or so historic occurrences have been observed. And so we're starting to get now to the point where we can think about a predictive subsurface model, and we can get away from looking at surface features and start to maybe build a recipe of where you might want to look away from this area by putting together the elements which we've been talking about, the hard rocks, the soft rocks, and the water. Now, I'm not saying this is the final answer. We're learning more all the time. We're a long way away from writing the playbook, as I mentioned earlier. And also there may be other locations where hydrogen is observed where this model doesn't work, and we have to come up with a different one. But it's a start, and it allows us to extend ourselves away from where the existing occurrences were. So, as I said earlier, most of us on this call today are probably soft rockers because we're AAPG folks. But I'd urge people to think very long and hard about the other elements of other parts of the pie, the soft rocks and the water, and the various skill sets and understandings that exist in those disciplines. And so, yeah, bringing people into the fold for this area I think is very important. Understanding how these all elements come together. This is the approach taken by KSERM, and Geoff referred to that earlier, which is the consortium with the Colorado School of Mines and USGS to start to put together a predictive model into where hydrogen may be observed in the anywhere really, not just the USA. So I encourage people to look into that that consortium and how you might be able to join and help. So wrapping it up, yeah, we can use the Midwest as a good little sandpit to play around and maybe test a predictive subsurface model with a bit more drilling and so forth. We can backfill the story of why the historical hydrogen occurrences are there, and using the hard rock, soft rock, and water hypothesis. The mid-continent rift seems to be a very important factor in this area, and so maybe that's a model that can be exported. And the next step really is to just get drilling. There's a lot of conferences and articles and seminars such as this, and it'd be really nice to have less of those and more drilling. And so that's the plan for 2024. And I think I'm done.
Thank you. That was really great. Now, I've noticed that we've had a number of questions in the Q&A, so I'd like to encourage people to look at the Q&A box because they've been answered in writing. But that said, Geoff or Avon, would you like to recap some of the ones that you think are potentially of major interest? While you're looking, I have a question. Okay, so it's so intriguing to look at the sort of hydrogen system in comparison with a petroleum system. And I did not hear any mention of thermal history or paleo heat maps or geothermal. Is there a relationship between the development of hydrogen, generation of hydrogen, and heat?
Yeah, I can jump in there. Yeah, absolutely. I mean, the temperature of generation of hydrogen or the rate of hydrogen generation is highly temperature dependent. And so these redox reactions are more favorable, especially the serpentinization type of reaction involving these peridotite type rocks. The rate is fastest at between maybe 200 and 250 degrees Celsius. That said, at lower temperatures, you still can get reactions. And so if you have geologic timescales, hundreds of thousands to millions of years, you can still get significant generation. So the heat flow and time are both factors similar to what we have for petroleum source rocks, where thermal maturity is a combination of time and temperature, right?
That's really interesting. And it makes me wonder, the second part, if there are any kind of pathfinder or indicator minerals or that would maybe reflect that perfect hydrogen generation history.
One thing that we're looking at the USGS is some advanced geochemical tools on the fluids themselves. And so we are, I'm quite interested in looking at the clumped isotopes of methane in hydrogen-rich gases, as I think that could very well be a strong indicator of the temperature of generation of that methane, which could be a proxy for the generation of hydrogen as well. And also, again, other just bulk isotopes of other gases, as well as clumped isotopes of other species like nitrogen, could be really important. And there's so much that we don't know at this point, that there's just a lot of work that we need to do. And I would echo what Avon has said, that we need to start drilling more wells and get more samples of fluids and start doing, getting more in-depth understanding of how these systems work.
That totally makes sense. Okay, so I'll start reading some of the chat questions. And also I'd like to encourage people to go ahead and unmute and ask questions if they'd like to, but here's Mary Herman Foley. Is there any intention to go back through the data to look for both hydrogen, but also looking at geothermal and the mineral potential, such as lithium, which is huge in Europe?
Avon, do you want to take that?
Yeah, look, it has popped up from time to time, the coexistence of lithium in the brines, particularly.
Well, I just talk it in. Yeah, there's just 260 people in there. I don't know.
Okay,
The
that's taken care of.
look, it's not something we particularly are directly targeting, but we're going to keep an eye out for. And anecdotally, it has been seen in the Western Interior Plains aquifer and locations in the fractured basement.
Okay.
Yeah, and I would add that I gave a talk a couple months ago at a geothermal conference about the potential for co-production of hydrogen with geothermal resources. And that also, I think, has a lot of potential, that a lot of geothermal operators they don't even look at the composition of the gases that they vent to the atmosphere. And in fact, they're throwing money away, that there's actually high concentrations of hydrogen. And in Iceland now, they have looked at some of the gases and realized that they could be making money by recovering hydrogen out of their effluent. So yeah, there's absolutely a lot of synergies there.
Oh, excellent. Okay, Franik Hashuk has asked, and by the way, he's the president of the Energy Minerals Division. So thank you, Franik. Is there any hydrogen stable isotope data available that might point to the possible source, meteoric water versus deep basin brine? ?
So there is a nice compilation paper from 2022 by Alexei Milkov, where he compiled all the published data on hydrogen isotopes of molecular hydrogen. I think that the interpretation of those data is challenging. There's the potential for exchange of hydrogen isotopes with water and other processes. If you have biotic or abiotic consumption of hydrogen, that can also fractionate the hydrogen isotope. So I would say there are data out there. It's still an open question as to how best to interpret them. And I think that this is an area where we need to do more like controlled experiments in the lab, and also have, very well constrained natural systems that we could then understand that with. But yeah, there's a lot that needs to be done there.
Okay. So, let's see, let's check out so many chat. If you guys want to choose one of the chat messages, I'm having a hard time selecting one.
Right.
Hey, Geoff, this is Wahid from Impact Exploration. I have a question for you, since Susan is finding more questions for you. You mentioned about helium and hydrogens, their molecular weight-wise and size-wise same. I probably disagree a little bit on that one, because it has huge differences, but not huge, but significant, at least 10-15% differences on height versus weight versus molecular size-wise. And have you ever done any research on Huguet and helium production versus hydrogen relationship? Huguet and gas field, where you have the helium.
Right. Yeah, I am familiar with the Hugoton gas field, and I have looked at gas chemistry from the Anadarko quite a bit. And we have not seen measurable amounts of hydrogen in any of those gases. And I think that the reason for that likely is that we have a lot of very viable petroleum source rocks in that basin. And so if their hydrogen was coming up from a deeper source, it was getting incorporated into the hydrocarbons there. And so the helium, of course, is inert, so it would move right through there and not be affected, but the hydrogen would be consumed. And on the helium question, I'm curious because from what I understand, the kinetic diameter of a hydrogen molecule is actually slightly smaller than a helium atom. And I have seen published studies of diffusivity helium and hydrogen through both shale and in water, where they're comparable, but in fact the helium is a little bit more diffusive. It really is dependent on this diameter size. So I would be interested if you have other data that contradicts that.
Yeah, just wondering, the molecular mass-wise, helium is a little bit different than the hydrogen. So
that's true. The mass-wise, that is true. Yes.
So if that mass-wise is different, it's almost one is a double of the another size. So I don't know whether it creates any problem, because mass is another thing. The gravity is going to work on anything, right? And
yeah, exactly.
Migration is going to be impacted by that. So of course, you guys are doing very massive research. I'd love to hear back from you at some point. Thank you, though. It was very nice talk, Geoff. Good seeing you all the time.
Okay, great. Thank you. Yeah.
Thanks, Wahid. So Damian Lynch and Sage Mutel both have questions that are sort of similar. So Damian says, one of the concerns with producing and transporting hydrogen is metal embrittlement. You show old wells that have been sampled over time. Is embrittlement an overblown issue?
Avon, do you have thoughts on that? Or?
I think it's well, put it this way, I haven't seen any examples of wells that have fallen apart due to hydrogen embrittlement. So either it's not there in sufficient concentrations to do it, or hasn't happened yet, or it's not a concern, and it's too early to tell.
And then and related to that, how do drilling operations have to be modified for hydrogen?
Once again, we're still learning, but it's probably the two things we need to think about really is what we do with the mud gas system and how we detect the hydrogen. Because when you're drilling for hydrogen, you can actually generate hydrogen through bit burn. So having some sort of mud gas system which corrects for ROP as you're drilling and measuring hydrogen at the same time needs to be factored in. And Schlumberger can help with that sort of stuff. Another thing we probably need to think a bit more about is cement mixtures, because we not only potentially embrittling steel, we could be embrittling the cement as well. So there's various recipes out there which are highly proprietary, but it's apart from that, we think it's just standard equipment.
A really good point about cement and cement integrity. Okay, so we have an anonymous participant who is expressing skepticism about Mali, I think. Anyway, any ideas about the actual flow rates from Mali hydrogen production?
Yeah, so I was just in a meeting this morning with a student who did his PhD work on the Mali accumulation, and he was discussing the production rates of that well. So I do have the latest data from that, and they are producing at about 1,500 cubic meters per day, which admittedly is not a huge quantity, but it's important to keep in mind that this is not a commercial type of field. This is not commercial production. That because of the geopolitics and the economics of the setting in Mali, they're unable to produce to sell more. They could produce more than they can, but they don't have a market for it. They don't have off takers right now, so they are only using it to power the village. As I mentioned, now they have this electrolyzer and they're using it to generate electricity for the village. But the numbers, the point being that the numbers of production numbers from that one well are really not very meaningful, because it's constrained by how much they can use and not by how much they can produce. So I think that that Gold Hydrogen, who's operating these Ramsey wells in the York Peninsula, they're in a different situation. They have off takers. They have plans to commercialize this, and so when they do their flow tests, they will be looking at what scale of commercial production can we get from these wells. And so those results will be meaningful for us.
Oh, great.
I've got a quick question, and that relates to surface gas sampling. Is there any way to put a bunch of gas sample traps out across the lower 48 and look at hydrogen concentration and see how it varies from atmospheric and look for sources that way?
Yes, and the short answer is yes, absolutely. And in fact, so we're working on that. I have a postdoc who's working with me at the USGS. Obviously, this is a big country, so you're not going to go out and sample every spot. And people are doing this and have been doing this for many years now. And one thing I can tell you is that it's highly heterogeneous, and so you could sample in one location and move just a few meters away and get a very different number. And so the strategy is actually to look at the geology, like Avon showed us, really nice approach for looking at the geology. Where is the fluid flowing? Where are the source rock? Where would it be generated? Where would it be moving to? And then once you have identified these areas that look like the elements are coming together that could generate a hydrogen accumulation. Then you want to go out to that area and start sampling around faults, or the places where you're most likely to find a flux of hydrogen, or springs, looking at not only hydrothermal springs, but just even cold springs, looking at gases dissolved in groundwaters and coming out through the subsurface. And then the other important consideration is that where you do find elevated hydrogen coming from the subsurface, that does not necessarily mean that that's the place you want to drill, that there's accumulation directly below that, but rather that's a confirmation that you do have some kind of active hydrogen system that's capable of generating hydrogen. And now you need to do more subsurface characterization to figure out where would the accumulations might be, and that would be the place you want to drill. Very likely it's going to be off from where you're actually seeing it coming out at the surface.
Great. Okay, so a couple of questions. We'll go on for a few more minutes. We won't go too long, but there's so much enthusiasm, and I just want to recap that. Remind everyone that you will be getting an email, and that will contain a link to the recording. I'll just need a few days to process it and do things like that. Okay, so has there been any H2 exploration around the Hartville uplift in Wyoming?
Not that I'm aware of. I don't know, Avon, do you know?
No, there are some historical occurrences in Wyoming, but I don't think they've been followed up in recent times.
So Bruce Black says, we have recently had a discovery in a wildcat well in the Rio Grande Rift. We are getting 11% hydrogen and 1% helium in the well. How do we capitalize on this? Wow.
Yeah, that's exciting. And I don't know, Avon, you might have a better sense of how to capitalize on a discovery like that.
Yeah, it's a really good question. It's something that investors get nervous about. So I would encourage people to look at something called the hydrogen ladder, which is sort of an off-taker's perspective of what to do with hydrogen once it's been generated or found or located. The best thing to do with hydrogen is to turn it into something else immediately as it exits the wellbore, whether that's ammonia, methanol, electricity. There's a multiple options there for industrial chemicals and feedstock. So transporting and storing hydrogen is something you don't want to get too involved in, given its difficulty to maintain in any storage vessel. So that's going to be location dependent, and also having access to other gases. So one of the nice things about Kansas, for instance, is that the gas mixture appears to be a mixture of hydrogen and nitrogen, which is what you need for ammonia generation. So depending on your locality, you'll probably come up with different answers, but yeah, the general thing to do is to turn it into something else ASAP.
That makes sense. Okay, Nicole Copeland is asking, I wonder if there are plans to directly test the mid-continent rift basement source in Kansas to compare against the Nemaha accumulation.
Yes.
Okay, that's good. Okay, let's see, we've got more. Any hydrogen and helium results you can share from the Nebraska and Geneva well? Do you think Kansas is more prospective than Nebraska?
So I have no results from Nebraska. That well is operated by Natural Hydrogen. And Avon, I don't know if you want to comment on that further, but
yeah, they're the operator, so they're the ones who need to have the questions directed to.
Okay, so Albert Mindy has had two questions. One is, what instruments do you use to measure hydrogen? And then also, would the East African Rift be a good place to explore for hydrogen?
So we have some electrochemical sensors. There are instruments that you can purchase, commercial hydrogen detectors that are based on electrochemical processes. And so we use those for looking at hydrogen. in soil gases. And then also we use mass spectrometry to confirm those identifications. And I think they take the same approach for the mud gas logging as well. With regard to the African rift, I would say I think it's prospective. There's certainly going to be the potential for hydrogen generation, whether you have the other elements for accumulations, reservoirs and traps and seals and so forth, would take more detailed work. And of course, you also have organic rich rocks that could be a risk for loss of hydrogen as well.
That's good. Okay, so Har Mohammadi asks, Geoff, do you think the tri-state area would be a potential sweet spot as the mineralization involved with the hydrothermal fluid flow and precipitation of heavy minerals?
I don't know where the tri-state area is. I think there's.
I think that's a tri-state lead zinc. That's part of the overall like Mississippian type mineralization in mid-continent.
But
that's Missouri, Northeast Oklahoma, Northwest Arkansas, Southeast Kansas.
Yeah. Okay. Yeah, I do think that would be very prospective area. Yeah.
Cool.
Yeah, and we'll have we're still working on our map, but I think that a lot of this will come out in that mapping exercise. Hopefully.
Nice. So Sherilyn Williams Stroud has mentioned that the University of Kansas and the University of Illinois are focusing on hydrogen. Very
okay.
Cool. Wow. Okay, so why don't you guys look through the different questions and select one that maybe okay, so Nick Sakharov is saying, let's discuss the following aspect. Hydrogen will mostly be used for long energy storage in off-grid smart grid systems. Shouldn't we then focus on hydrogen only in the areas where the demand is?
Well, it depends on what you want to do with the hydrogen. Like I previously said, the chemical feedstock route is probably the lowest hanging fruit to get after. Absolutely. But if you can find it where the demand is, well, then maybe you look at being a direct energy source. We just got to find it first. That's the first challenge. And then we'll find it in a location we like even more later.
Yeah, I think what Avon was saying earlier about transporting hydrogen as hydrogen itself is really not efficient. You want to avoid that at all costs. But if you can convert it to something else or use it on site, then that's the way to do it. And I know companies that are working in Arizona have told me that they've been finding hydrogen, and they plan to convert it to methanol and ship it to the port of LA to sell to the shipping industry to fuel marine vessels. So there are a lot of different ways to use hydrogen going forward.
Well, okay, one final two questions. What are the challenges met with when there is a faulting system, and how do you tackle those challenges?
I guess it depends on your exploration paradigm. Some people like to go for faults, particularly in fractured basement because of the system porosity and permeability. Other people want to stay away because there's too much water involved. I think our play models are still developing, and it's going to depend on which one you prefer as to whether you're going to avoid faults or actually target them. We'll know in a year or two.
Interesting. Okay, final question. Do we know whether the generation in Kansas, Mali, South Australia is simply an accumulated hydrogen, or does it replenish, meaning that it keeps charging in present day? And then how do we know?
So I can speak to the Mali case where they have actually recorded that the pressure they're producing out of the shallowest reservoir. As I mentioned, there's at least 5 stacked reservoirs, and they're producing out of the shallowest one, And they've been producing now for 10 years. And the pressure in that reservoir has actually gone up, has not gone down. And the concentration of hydrogen has also stayed constant. And what they think is happening in the deeper reservoirs, it's actually, there's not a free gas phase. It's actually water saturated with hydrogen. And so they think that as they're withdrawing gas from this upper reservoir, that it's exsolving from the water and migrating up and recharging that reservoir. But that doesn't mean that it's presently being generated. It's just simply coming out of aqueous solution there. And also the rate of withdrawal is really not that great. So you know, I don't think that model would hold for other situations. Beyond that, I don't think we know. I mean, Avon, maybe you have other information, but I don't think we know anywhere else about rates of generation. Yeah.
No, not really. The only thing I could point to in the area I was talking about earlier is the fact that those historic wells, or particularly Scott and Hines, seem to maintain their hydrogen concentration through time. Given it's a very reactive gas, you know, you've got to ask questions about perhaps replenishment is occurring there, or there's some other secondary factor which is preventing the hydrogen from converting to methane or water again. So it's pretty feeble evidence, but it's something to think about.
Thank you. Well, okay, so I think we're pretty much up to our time commitment. We've gone over about by 11 minutes. I want to thank everyone for the questions. So we can't get to all of the questions or comments. So I'd like to encourage everyone to email Geoff or Avon, and we'll see what they. So that will be one way to be in touch. And also, I'd like to encourage everyone to join the APG Division of Environmental Geosciences. We've got Bert Vogler, who's our president, online, and also Franek Hashuk, who's our president of Energy Minerals Division. And we have a hydrogen committee, and Geoff is very active in that. And I think that we're also planning a hydrogen special session at Image in late August. So there are many reasons to stay engaged with APG and learn more about hydrogen. And I just want to say thank you again to Evan McIntyre and also to Geoff Ellis for being our special presenters.
My pleasure.
Thanks, Susan.
Thank you.